Welcome back, everybody. Now to our discussion of power. Yet another word in physics that appears in your everyday life but has a little bit different definition than in your everyday life. The definition that we'll be working with for power is a rate at which work is done or energy is transformed from one type of energy to another type. Now we've already looked at how to calculate work and how to calculate energy. All we're adding to this is this idea of the rate. Now, we've worked with rates before. The rate at which you change from one position to another was our velocity. The rate at which velocity changes we called the acceleration, and in both cases we're just taking that quantity and dividing by the amount of time it takes to change by a certain amount. The same is true with power. We have three equations that we work with regularly for power. The first two are really just the same thing with slightly different symbols. So first off, we can think of power as being the amount of work done divided by the amount of work that it takes to do that. Divided by the amount of time it takes to do that work. So we do work divided by delta t. Now if they don't give you work in a problem, of course we could calculate work by doing force times displacement. The second form of that equation, delta E over delta T, is just how much energy is changed from one form to another. And again, we've worked with these other equations for gravitational potential energy, and elastic potential energy, and kinetic energy. So we can use those equations to figure out how much energy has been changed from one form to another. For example, you might be given a problem where a car is accelerating from one speed to another, and the question would be about how much power the engine had, or the engine was using to accelerate the car. Well, we'd just be converting between the kinetic energy we had initially and the kinetic energy we have in our final state. That tells us how much our energy has changed, divided by the amount of time it takes to make that change, would give us our power. An equivalent form for power is force times velocity, which comes from this equation, actually. Work is the same as force times displacement. Displacement divided by time is just velocity, so force times velocity. Now we can actually use this equation regardless of what our force and our velocity are, or whether they change over time, but it requires calculus to do it. For our purposes in this non-calculus based physics class, we'll only use this problem when force and velocity are constant. And notice that this isn't the net force acting on an object. This is an individual force. So how much power that individual force, or that one object that's applying the force, is using to maintain this velocity at a constant rate. Now, if we used the net force in this equation, since velocity has to remain constant for this to work, net force would just be 0, so our power would be 0 as well, which will be the net power, but not something we're typically interested in calculating. As far as units go, with power, the one we use most frequently is watts. This is one that you would have seen before with light bulbs or appliances, are measured, have their power measured in watts. A watt is an abbreviated unit, just like joules and newtons were. So watts are equivalent to joules per second, or J/S, or SEC if you have lousy handwriting like I do. The base units down here for watts would be kilogram meters squared per second cubed, which is a strange unit to use, and it's a lot to write every time. So we really just stick with the abbreviated versions of this. But sometimes it's useful to know the base units for when we need to do these calculations and cancel units out, figure out what units our answer is going to be in. Maybe a more common unit for power that you would have heard would be the horsepower unit, which used to be based on how much power a horse could apply to a given situation when it's pulling. Now it's just a standard unit, though. It's right around 746 watts to 1 horsepower. So if you gave the power rating of an engine in horsepower, that number would be a lot smaller than the engine rating in watts. And so cars, car engines, and engines in general in the United States have their power expressed in horsepower. We stick with watts, though, because that's the SI unit. So if we're given something in horsepower. We'll just use this conversion factor to put it into watts. Now let's do a couple example problems with this. We'll start with a simple one. How many joules of electrical energy does a 60-watt light bulb convert in an hour? Well, we know that the 60 watts for that light bulb, that's got to be the power, because watts is a unit for power. An hour must be our unit, or must be our time. We'll have to convert that to make it the base unit, so we'll convert it to seconds, but it's a pretty straightforward calculation. We can kind of reason our way through it, though, based on the meaning for watts. 60 watts is the same as 60 joules every second. So 60 joules of electricity come into that light bulb every second, and the light bulb converts it. Now, depending on what kind of a light bulb we're talking about, we have different amounts of that energy turning into different new types of energy. With those older incandescent light bulbs, those were often something like 10 to 20% efficient, which meant that 10 to 20% of our energy gets converted into light. The rest, in general, gets converted to heat. So not very efficient systems. That's why those new compact fluorescent bulbs are so much better. They're much more efficient. More of that energy turns into light and less into heat. So 60 joules every second. How many in an hour, then, is the question. So we always start on these by writing out our given information. Power is 60 watts. Our time is 1 hour, which is the same as 3,600 seconds. And we're looking for delta E, the amount of energy converted in that time period. The equation then that we'll be using is power is equal to delta E over delta T. We're looking for delta E, so we'll isolate that in the equation, multiply both sides by delta T. Get that over to the other side, that will cancel, and we get delta T times P equals delta E. So our energy, amount of energy changed from one form to another, is going to be equal to our time, which is 3,600 seconds, times the power, 60 watts, which gives us 216,000 joules. Or when we round to just one sig fig on this one, we'll make that 200,000 joules of energy converted every hour, which is a large amount of energy, and this would be the reason that we are always encouraged to turn off lights in rooms that we're not using, of course. Next, we'll look at a little bit more detailed example, or at least a little bit more that goes into this one. Here, we're trying to lift up an object, a piece of a building, using a crane. We're given the power rating for the crane is 53 kilowatts, or 53,000 watts. We're given the mass of the building, but we don't know anything about force here. So that tells us we're going to have to go back to some of the stuff from the last chapter to figure out what the force acting on this building piece is. We're trying to lift it 38 meters at a constant velocity. So we start with our given information. Got our power, it's 53,000 watts, mass is 1,200 kilograms. We're lifting at a distance of 38 meters, and depending on what equation we use, we've seen a couple of different variables that could be applicable here. We could use delta x, the displacement, d, the distance, or h, the height, and all those would be 38 meters. It told us in the problem we were going to lift at a constant velocity, so acceleration is 0, and we're looking for the time required to make this happen. Now, in this problem, I'm going to be using my work equations and my power equations together. So power is work divided by time, but I don't know how much work I've done. So that'll be my first step in solving this. Need to get work before I can solve this one for time. So first, work is equal to force times distance or displacement, F times d anyway. Here again, we aren't given any information about force, so we'll have to figure out how much force would need to be applied to this 1,200 kilogram mass to lift it up at a constant velocity. Let's go to a free body diagram for that. We'll have two forces acting on this. The force from gravity going downward, and the force from the crane going upward. Since we're moving this at a constant velocity, or acceleration is 0, we know that the force from the crane will be exactly equal to the force from gravity on this building piece. If we wanted to move this up at an accelerating rate, getting faster, we'd need to have a larger force from the crane than the force from gravity. But constant rate, we need these to balance out exactly. So our force from the crane is going to equal the force from gravity, which is going to equal the same, equal mass times acceleration of gravity, which gives us 11,760 newtons. From here we can calculate the work done, 11,760 newtons, times the distance is 38 meters, which gives us a work done of 446,880 joules. And since we're looking for time in this equation up here, we know power, we know work. All we need to do is rearrange to get time by itself. We can't do that when time's in the denominator of the fraction, so let's start by multiplying both sides by delta t. Delta t will cancel over there, and we get delta t times p equals w. I want delta t by itself, so to get p over on the other side, divide both sides by p. P's cancel on the left, and we get work divided by power for our equation. So our time is going to be our work, 446,880 joules, divided by the power, 53,000 watts, or 53,000 joules per second. Might be a better unit to use here since we're working with joules and we want our answer to come out in seconds. We can see that the units cancel appropriately. And we'll get an answer here, rounded to 2 sig figs, of 8.4 seconds. Alternatively, you could have solved this problem using the potential energy equation. Instead of the form power equals work divided by delta t, we could have used power equals delta E over delta t, where our change in energy is going to be how much potential energy our object gains as it climbs up, or as it is raised up the 38 meters. So this would be power equals change in potential energy divided by time, or power equals mass times gravity times height divided by time. Again, we'd rearrange, get time by itself, and we have an equation for time of delta t equals mass times gravity times height divided by power. Either way, we do the same calculations and we come up with the same answer, so use whichever method is most comfortable for you. Thanks for watching. I hope this was helpful.